galvanometer. Okay. So in the
Okay.
moving coil name, from the name you can just guess moving coil. There is
Yes.
there will be some coil, and that coil will be moving coil like this. Rotate. The coil will perform the rotational motion like this. So what will
Yes.
happen? What will happen? You will have a coil, and this coil is placed in the magnetic field, and this
Yes.
coil is somehow the part of the galvanometer. Okay, so when there will be the current in the galvanometer, so there will be the current in the coil also. Okay, because this coil is a part of the galvanometer, and this
Yes. Yes.
coil is in the magnetic field also. What will happen? There are two magnets. One magnet is like this, means see, these are the two magnets. In between these two magnets, this coil is placed. Okay, one
Yes, sir.
magnet is this, another is this. So due to the two magnets, there will be the magnetic field, and when there will be the current in the coil, this coil will rotate, and a pointer will be attached somehow. A pointer will be attached with that coil, and there will be some deflection when the current is in the coil or in the galvanometer, because coil is the part of the galvanometer. So basically, see this figure. From this figure, you will get. So this is a cylinder. This is a cylinder.
Yes.
Okay, and on this cylinder, a number of turns of the wire are there. So this is known as the coil. Okay, so a type of cylinder, and you have bounded the wire like this,
Yes.
like this. Okay, and so this becomes the coil. This is a coil, and this is a rectangular coil here.
Yes.
Okay, first thing is a cylinder. On the cylinder, the wire is bound, and this wire bonding of the wire is this called as coil, and this coil has n number of turns. And now, what is the thing here? These are the magnets, horseshoe magnets. These are known as HORSE horse
Yes,
shoe
sir. Yes.
magnets, and
Yes, sir.
this setup is placed in the magnetic field of, and these are the magnets. So these magnets will produce the magnetic field, and this setup
Yes,
is
sir.
placed in the magnetic field. Okay, and due
Okay.
to the magnetic field, what will happen? The coil will rotate when there will be the current in the coil, or indirectly you can say there will be the current in the galvanometer, because this is the interior of the galvanometer.
Yes, sir.
So we have to see the interior mechanism, what is happening inside the galvanometer. And there are certain number of things that we will discuss here. So basically what will happen, this coil will rotate like this due to the magnetic field, and a pointer is attached. So when this cylinder will rotate due to the coil, due to the torque on the coil, the cylinder will also rotate, because that coil is attached to the cylinder. And when the coil will rotate, this pointer will rotate, and this pointer will give you the deflection, and you can just see the detection of the current can be done. Okay, you can detect whether the current in the circuit or not.
Okay.
So see here, what is the galvanometer? Galvanometer is a device used to detect the current and voltages, not to measure the sufficient amount of current, just to detect the current in the circuit. And how the current will be detected? When the current will flow in the galvanometer, there is a coil in the galvanometer. There will be
Yes,
current.
sir.
There will be current in the coil. Okay, and that coil is
Okay.
placed in the magnetic field. And due to the magnetic field, there will be the torque. Due to the torque, the coil will rotate. A pointer is attached with respect to that coil or cylinder. That pointer will deflect like this. So you
Yes,
can
sir.
just consider that there will be some current. Okay, so what is the principle? I have told you, a current carrying coil in magnetic field experience a torque. Simple. So this is the top view of the galvanometer. Top view means when this is the suppose galvanometer, you will see like this. This is the top view. You are
Yes, sir.
watching from the top. Suppose this is my
Okay,
hand.
sir.
This is the
Yes, sir.
pen here I have placed, and you are watching, not pen. This is the book
Yes,
here,
sir.
and top view means your galvanometer is this, and eyes are here. You are
Okay, sir.
watching on from the top, so you will get the image of this like this. This is now the top view, like this. Here you will see a
This is the
cylinder will
front
be this.
view.
No, this is not the front view. This is the
Oh,
top view. Okay, this
okay,
is the
sir.
top view. You are watching the galvanometer, from the
Yes, sir.
top. Okay.
Okay, sir.
So this will be looked when you will
Yes,
watch
sir.
this from the top. This a circle will be looked like this. The circle is representing the cylinder, and this is the wiring. This is the wire bound on this cylinder. So this yellow things is representing the wire is bounded on the cylinder.
Okay, sir.
And these are the magnets. These are the horseshoe magnets. Due to these magnets, this is the magnetic field, and this is a special type of magnetic field. We will discuss that what is this magnetic field and why this magnetic field is here. This type of magnetic field. This type of magnetic field is called the radial magnetic field. So this is the cylinder. This is the number of turns of coil. This is the number of turns of the coil on the cylinder, and this is the magnetic field due to these magnets. And a pointer is attached with respect to the cylinder, and when there will be the current, this pointer will deflect. So you will get there will be some current in the galvanometer. That is why this pointer is deflecting. Okay, so all the terms I have written here. This is cylindrical soft iron core in radial magnetic field. Now we will discuss what is the radial magnetic field and coil of n turns. Okay, this is the coil of n turns. This thing,
Yes, sir. Yes, sir.
coil of n turns. You can remove this. Okay, so I am writing here what is the radial magnetic field. Actually, radial magnetic field means always the angle between the means your alpha will be 90 degree always due to radial magnetic field. Alpha is the angle between the magnetic field and the magnetic moment. Okay, alpha is the
Okay, sir.
angle between the magnetic field and the magnetic moment. So now see, this can be understood by this example. So suppose your magnetic field is not radial. Your magnetic field is like this. Your magnetic field is this is the radial magnetic field. So see the magnetic field line like this, and like this. But suppose if your magnetic field is like this type of magnetic field you have only, and your coil is placed in this type of magnetic field. So in this type of magnetic field, when this coil will rotate, the alpha will not remain 90 degree always. At different point, there will be the different value of alpha. So see, this is your coil. This is
Yes,
your
sir.
coil, and this coil is in the magnetic field, and that magnetic field is the horizontal magnetic field, or you can say magnetic field in along the x-axis only. This type of
Yes, sir.
magnetic field. So you can
Yes, sir.
imagine magnetic field lines are like this, like this, like this.
Okay, sir.
So this is the direction of the magnetic moment. This pen is representing the direction of magnetic moment because magnetic moment is perpendicular to the plane of the coil. So this is the magnetic moment. So and
Yes.
magnetic field is like this here. So this
Yes,
time
sir.
the angle between the magnetic moment and the magnetic field is 0 degree. But what happens? The radial magnetic field is like that. If your coil will turn like this, suppose your coil is turning like this.
Yes, sir.
This is the direction of the magnetic field. Due to the radial magnetic field, that radial magnetic field will be like this in this direction.
Okay, sir.
And when your coil will move like this, so radial magnetic field will be like this also.
Yes, sir.
Okay, because the magnetic field lines are arranged in that way, or the magnetic field is like that. In that case, alpha always remain 90 degree. Angle between the magnetic field and the magnetic moment will always remain 90 degree. So this is the construction. A pointer is there,
Yes,
and
sir.
here is a cylindrical iron core on which a wire is bound.
Yes.
Two magnets are there. This is the radial magnetic field. You can say this part. These magnetic field lines are of radial magnetic field.
So what is the in the coil?
Hmm?
In the coil, sir? Like what is in the coil?
Okay, I will tell you.
Okay, sir.
In the core,
Yes,
In the
sir.
core, generally we place the soft iron core. We
Okay,
take a
sir.
cylinder. In the core, we
Yes, sir.
insert. Suppose this is a hollow cylinder. Here is a
Yes, sir.
hollow cylinder. In the hollow cylinder, you will insert a soft iron, a material of soft iron. Due to what will happen due to that? Due to that, there will be the increase in the magnetic field. We will discuss that.
Okay,
Hmm.
sir.
Hmm. So now some terms related to this. See this coil. There will be some area of the coil. So A is the area of cross section of each turn of the coil.
Okay, sir.
B is the strength of the magnetic field.
Yes, sir.
Strength of the magnetic field. Okay, simple. Current through the galvanometer. Okay,
Yes,
current
sir.
through the galvanometer. Deflection in the galvanometer. This pointer is representing the deflection. This theta is the deflection.
Okay, sir.
Okay. And M is the magnetic moment of the coil. Already know magnetic moment of the coil is
Yes, sir.
given by number of turns in the coil, current into
Yes,
area.
sir.
Okay. From here, theory and working is started.
Okay, sir.
In exam, you will draw only this part.
Yes, sir.
I think that would be sufficient. Okay,
Yeah,
so
yes.
now we will discuss the physics behind it. What is happening? We will write the magnetic moment and all that, and we will see what is happening. So this now it is clear that there is a coil, and that coil is in the magnetic field. Okay. So due to that magnetic field, there will be the torque on the coil already discussed. There will be the
Yes,
torque
sir.
on the coil. And torque on the coil is given by mb sin alpha. Okay, mb sin alpha, and this formula is valid for n is equal to 1. When there is n number of turns, so what you will say, this n will be multiplied, and mb sin theta, this formula will become sin alpha, not theta. So this is a torque acting on the coil due to the magnetic field. Is it or not?
Yes, sir.
And we know that alpha is equal to what? Alpha is equal to, see here,
Yeah, yes.
90 or what?
90, 90,
90
right?
due to radial magnetic field.
Yes, sir. Okay.
Alpha is 90 due to radial magnetic field. So here
Okay.
we will put alpha is equal to 90,
Yes, sir.
and we will write the reason in bracket. So we will put sin 90. So this will become sin 90 is 1 below. So this will become n m p. And magnetic moment is given by ia.
Yes, sir.
Magnetic moment is given by ia. Uh, wait, just a minute. Number of turns. Now
Yes, sir.
magnetic moment is ia. So here we will take the magnetic moment for one coil,
Okay, sir.
ia, because we have already included the n here,
Okay,
ia,
sir.
and this will
Okay.
become b. So total torque will be ni ab.
Okay, sir.
This is your equation number 1. What is this? Torque on a coil by the magnetic field.
Yes.
Okay. So what will happen now? When this coil will rotate,
Yes.
due to the torque, the coil will rotate. Due to the torque, the coil will rotate like
Yes,
this.
sir.
And a spring is attached. from here, from
Yes,
some
sir.
point, you can
Yes,
say
sir.
the spring is attached, like this is the spring, this is spring is attached. When this
Yes, sir.
coil will rotate, the spring will try to oppose the motion of the coil. From here, the spring, this coil is rotating like this, and the
Yes, sir.
spring is trying to rotate the coil like this. So there will be the restoring torque. There will be the restoring torque on the coil due to the spring. Okay.
Okay, sir. So it will try to make it move in the opposite direction.
Yeah. Try to,
Okay.
try to move the coil in the opposite. Means you can say oppose the motion.
Okay, sir.
So suppose K, there is a term K. K is the restoring torque per unit twist of spring when coil is rotated by angle theta. So what is K? A new term I have defined here, restoring torque per unit twist of a spring when coil is rotated by an angle theta. Mm, hmm. So when for the unit twist, see the statement, restoring torque per unit twist of spring. Means for the unit twist of spring, the coil will rotate like this, spring will try to rotate the coil in the opposite direction. Means the spring is twisting,
Yes, sir.
spring will twist like this. So there will be the twist, there will be the twist in the spring. For the unit twist, the restoring torque in the spring is K. For the
Yes,
unit
sir.
twist, the restoring torque in the spring is K. Twist means the amount of angle the spring is rotating, that is twist in the spring.
Okay, sir.
Now per unit twist in the spring. So what will happen when your coil is rotated to an angle of theta? Your coil is rotated to an angle of theta. Same, your spring will try to move in the opposite direction, to an angle of theta. Means your spring is twisting to an angle of theta. So for unit twist, the torque is K. For theta twist, the torque is K theta. Is it or not? Okay, just I am writing. So you can say restoring torque due to a spring in coil, due to a spring you can write. That restoring torque is represented by tau suffix r. I have told you torque is represented by tau. So that
Yes, sir.
restoring torque is given by tau suffix r, and that is given by K theta. Because what is K? K is the torque for the unit twist, and for the theta
Yes,
twist,
sir.
torque will be K theta, unitary method. Unitary method. Okay. Now coil is rotating like this, spring is trying to rotate the coil in the opposite direction. So what will happen? There will be a time when there will be the equilibrium. Means the amount of torque due to the magnetic field is balanced by the amount of opposite torque by the spring. So you can say in equilibrium T is equal to TR. दोनों टॉर्क इक्वल हो जाएंगे. ओके,
Okay,
both
sir.
the torque will be equal.
All right.
So now we will put the value, this torque, this tau is from here and IAB. What is tau R? K theta.
Yes, sir.
Very good. Now from here we want current. What is the current in the galvanometer and how the current will depend? So the current,
Sir, I, right?
yeah, current is I. I
Yes.
think I have this. This is the I. I is representing the current through the galvanometer. Okay.
Yes, sir.
Yeah. So current will be given by K theta divided by
NI.
and
Oh.
AB. Okay.
Okay, because we took already I. Yeah. Okay.
Now K is the spring, means the restoring torque per unit twist, and this K has one another name also, torsional constant. Torsion is produced now when, suppose I have just torsion. What is torsion? See, suppose this is a pen and I have just kept this pen from here. Okay,
Yes.
like this from my hand. मैंने यहाँ से इस पेन को पकड़ लिया.
Okay.
अब देखना. Now what will happen? I am just trying to rotate this pen.
Yes, sir.
But this pen is not rotating because this is fixed from here. This pen is fixed from this end. But what
Yes, sir.
will happen that when we will try to rotate this pen, there will be some torque in the opposite direction produced inside this pen. That torque is known as the torsion. Torsion
Okay,
means,
sir.
yeah. So torsional constant will be there because for the spring there will be also the same case. For the spring, what will happen? The coil will try to rotate the spring in this direction.
Yes.
But the spring, in the spring there will be the restoring torque. Torsion in the
Yes,
spring will be there
restoring torque.
in the opposite direction.
Okay, sir.
And that is why this is also known as the torsional constant.
Okay, sir.
So this current is given by K theta divided by NAB. So we have taken the spring already, means the material of the spring is decided. So your K is constant. For a given galvanometer, your K will be remain constant because the material is already decided. Number
Yes.
of turns in the coil is already decided constant. If you suppose you have purchased one galvanometer from the market, you cannot change the material of the galvanometer. You cannot change the number of turns in the galvanometer. You have a
Yes.
fan here, you have a fan here. Can you change the number of turns of the coil of the fan? No, we
No, sir.
cannot change. We can only change the supply of the electricity.
Yes, sir.
We can change current. We can change. Okay.
Yes.
So there also we cannot change the number of turns. Area we cannot change. Magnetic field we cannot change. So magnetic field is radial. Okay, this will also remain constant. So your current will only depend upon theta.
Okay, sir.
What is the meaning of this? When there will be the current in the galvanometer, there will be some deflection theta in the galvanometer.
Yes, sir.
And already discussed all the things. I means current. I means current. Theta is the deflection in the galvanometer. Okay. Whenever you are getting confused in the symbols, just
Yes,
see
sir.
somewhere I have written. I know that. I have
Okay.
written somewhere the meaning of the symbol, but you have to search because again and again I cannot write. Okay, because this will take our time. So you can say the current in the galvanometer is directly proportional to the deflection in the galvanometer. The more the current, more will be the deflection in the galvanometer.
Yes, sir.
So this is the galvanometer, working of the galvanometer theory and all that you can say. Means now you can do the questions from this part. Means the examiner can ask you write the principle, construction and working of the moving coil galvanometer. Very simple. A coil is there. On that coil there is a torque and just copy this.
Okay, sir.
Take this.
Done, sir.
Question part completed. This.
Yes, sir. Done, sir.
Okay.
Done, sir. Okay, done, sir.
Okay. Now we have simple topic like current and the voltage sensitivity related to this topic. Current sensitivity and the voltage sensitivity. So current sensitivity is represented by I suffix s. Current sensitivity means the amount of current flowing in the galvanometer, and we will see how much there will be the deflection in the galvanometer. So current sensitivity is given by the uh, deflection in the galvanometer divided by the current in the galvanometer. You can say deflection per unit current in the galvanometer. Theta, this current, this. And from here, we can calculate the current sensitivity. What is current sensitivity? Theta by I. So put the value of current sensitivity theta I. We can get I from here. K theta divided by NAV. From here, this theta and theta will be removed.
Yes.
And your current sensitivity. This will be in the numerator
Any.
by K.
Okay, sir.
Simple. So now you have to see this current sensitivity is depending upon n. There are number of terms. A n, area of cross section, magnetic field, and K is the torsional constant or restoring torque per unit twist in the spring. So if I want to increase the current sensitivity, what I will do? I will just increase the number of turns. I will increase the area. I will increase the
Yes, sir.
magnetic field. I will decrease the torsional constant. So see what will the effect on the galvanometer when we will do these types of things. How to increase the current sensitivity? Current sensitivity is depending upon these terms. Means current sensitivity is directly proportional to number of turns. Okay, so if you will increase the number of turns of the coil in the galvanometer, what will happen?
Yes.
Current sensitivity will increase.
If we increase
Okay,
the number of turns,
then current sensitivity will increase because current sensitivity is directly
yes.
proportional to the number of turns. Okay,
Okay, yes, sir. Yes.
Hmm. But I'm just writing it like this: current sensitivity, or you can write number of turns when you will increase. This is a symbol of increase. Hmm. So
Yes,
your
sir.
current
Okay.
sensitivity will increase.
So for decreasing, it will be down or arrow, right? Okay, sir.
Now, what will happen when you will increase the number of turns in the galvanometer? The galvanometer become very bulky. You cannot increase the number of turns of the coil in the galvanometer beyond a certain limit. Because if you will increase the number of turns again and again, it will require more area, more space. Your galvanometer will become bulky. So here we can write number of turn cannot be increased beyond certain limits. Otherwise, otherwise, uh, okay. Now increase the area of the coil. Area of the coil. So you can increase the area of the coil. If you will increase the area of the coil, then your current sensitivity will increase. Now, magnetic field, your point you are saying why, means what is soft iron core and why we are placing the soft iron core. Okay, so this is the point. So see here
Okay,
now,
sir.
focus on this.
Yes, sir.
This current sensitivity is directly proportional to the magnetic field. And how we will increase the magnetic field? We will insert a soft iron core inside the cylinder on which the wire is bounded.
Okay, sir.
So your current sensitivity will increase, or you can say when you will increase the magnetic field, magnetic field will increase,
Yes.
then your current sensitivity will increase. But how you will increase the magnetic field? You will
Number.
use soft iron core.
Okay, sir.
Like here we have used the soft iron core. In the galvanometer, I have just written that.
Yes.
For the K value, current sensitivity is inversely proportional. So for this, if you will increase this, so this current sensitivity will decrease. If you will
Okay,
increase
sir.
this will decrease. So you can write here when you will decrease current sensitivity, torsional constant, then your current sensitivity will. So how you will decrease the torsional constant? You will torsional constant depending upon the material only. So you will choose the material of the spring whose torsional constant is small. Okay. So
Okay, sir.
using spring of low torsional constant, spring of low torsional constant, and low torsional constant material is the material. This is the material we have: phosphorus bronze strip, PHOS, PHOROUS, bronze, phosphorus bronze strip we will use for the spring.
Okay, sir.
Now voltage sensitivity, simple, same thing, means not same thing, but we can derive with this formula of current sensitivity. So voltage sensitivity, current sensitivity was deflection per unit current, voltage sensitivity, deflection per unit voltage in the galvanometer. So see, voltage sensitivity is V suffix S, deflection per unit voltage of the galvanometer. So voltage sensitivity is given by theta divided by V, and V is the voltage drop in the galvanometer. We know that V is equal to okay. We can write, we know that this V is equal to IR. V is equal to IR, we know that from the Ohm's law, means V is equal to IR, na? We know that. So we will put this value here. Vs is equal to theta current into resistance. So put the value of current here from here. What is the value of current? K theta divided by NAB.
Yes, sir.
This theta and theta will be removed. Voltage sensitivity will be NAB divided by K into R. So now see on what factors the voltage sensitivity is depending. So voltage sensitivity is depending upon the number of turns. area, magnetic field inversely proportional to the torsional constant and the resistance of the wire of the coil you have. Okay. So how
Yes,
you
sir.
will increase the how you will increase the voltage sensitivity? You can increase the number of turns, you can increase the area, you can increase the magnetic field. These points
Yes,
will
sir.
remain same like this. Increase the area, magnetic field, and the number of turns. But no, just a minute. When you will increase the area, voltage sensitivity will increase. When you will
Yes, sir.
increase the magnetic field, voltage sensitivity will increase. When you
Yes,
will
sir.
decrease the torsional constant, voltage sensitivity will increase.
Yes, sir.
And how you will increase the magnetic field? You will use a soft iron core.
Yes, sir.
How you will decrease the torsional constant? You will use the material of low
Sir.
torsional constant, that is phosphorus bronze strip.
Yes, sir.
Now see, when you are increasing the number of turns, what will happen? On increasing the number of turns, the amount of wire will increase. If you are increasing the number of turns, the amount of wire will increase. If
Yes,
the
sir.
amount of wire is increasing, means the resistance of the wire will increase. So this will, if you will increase this, so this will also increase. Means there will be no effect when you will increase the number of turns, because voltage sensitivity is inversely proportional to the resistance. When you will increase the number of turns, then your resistance will be increased. So this N by R ratio will remain same. So how to increase the voltage sensitivity? These are the terms I have written here. Okay.
Okay, sir.
So you can write here voltage sensitivity inversely proportional to K also. So for this, Vs is directly proportional to N by R. So N by R I have taken. On increasing the number of turns of the coil of the galvanometer, resistance of the coil increases simply. So current sensitivity is directly proportional to the number of turns. On increase in number of turns, Is will increase. Okay. Now I am talking about the current sensitivity here. Current on increase in the number of turns, current sensitivity will increase, but voltage sensitivity will not increase because of this. Because voltage sensitivity is directly proportional to the number of turns, but inversely proportional to the resistance. You will increase and R will also increase. This is increasing. This is increasing. Means this ratio will
Yes,
remain
sir.
constant. Means your voltage sensitivity will remain constant. So Vs will remain same. So this is the funda.
Okay,
Okay,
sir.
just note down.
Okay, sir. Done, sir. Done, sir.
Hmm.
Done, sir.
Done.
Yes, sir. Done, sir.
Hmm.
Done, sir.
Now, this formula you should know. Okay. So one question based on this. Okay. Suppose you don't know this formula. Okay. So coil of galvanometer is of area this.
Yes, sir.
It consists of 200 tons in magnetic field of 0.2 Tesla. Torsional constant is 10 to the power minus 6 Newton meter per degree. Torsional
Yes.
constant means K is given. All the terms I have written here, those are given in the question. So after that, what is they are asking what is the maximum current that can be measured by the galvanometer? That can be measured by the galvanometer if the scale can accommodate 30-degree deflection. If the scale can accommodate means the deflection of the pointer will be maximum to 30 degree only.
Yes.
Now, suppose I don't know what will be the current, but I know that at equilibrium, T is equal to TR,
Yes, sir.
torque due to the magnetic field is equal to torque due to the spring. Torque due to the magnetic field is given by NIAB, and torque due to the spring is K theta. So current I can find from here K theta divided by NAB.
Any, yes.
Now this K I have told you was constant, N constant, A constant, B constant. So your current is depending upon theta. So if your theta is maximum, then your current will be maximum. You can write here. They are asking the maximum current. Na? What is the
Yes,
maximum current that can
yes.
be measured? So current will be maximum when theta will be maximum. Put all the values. Put the value of K here, 10 to the power minus 6. What is theta maximum? If the scale can accommodate 30-degree deflection, means the maximum deflection for the pointer or maximum theta will be 30 degree. You will put theta max is given by 30 degree. So you will put this theta 30, number of turns 200, area is also given 0.02, 0.08. Okay.
Okay, sir.
And magnetic field is 0.2 Tesla. You will get the current some value in ampere when you will calculate this.
Okay, sir.
Second part. In the second part, they are asking what is the smallest current that can be detected if the minimum observable deflection is 0.1 degree. Means the minimum deflection of the galvanometer or the minimum value of theta will be 0.1 degree. So
Yes,
your
sir.
current will be minimum when your theta will be minimum.
Yes, sir.
So you can write current will be minimum when this K into theta minimum, and we put all the values. Theta is 0.1 or 0.01, 0.1 degree divided by number of turns 200, area multiplied by magnetic field is 0.2 Tesla, and your here theta minimum is given, that is 0.1 degree. You will get some value in ampere. Now copy this.
Okay, sir. Done, sir. Done, sir.
So in the starting, I have told you the galvanometer is just to use to detect the current, not to measure the significant amount of current. Very small current we can measure from the galvanometer, but not the significant amount of current we can measure from the galvanometer. So the examiner will ask you why the galvanometer is not able to or why we cannot measure the current from the galvanometer, or why we cannot measure the voltage from the galvanometer. For that purpose, what we will do, we will convert that galvanometer into ammeter for measuring the current. For measuring the voltage, we will convert that galvanometer into voltmeter.
Okay, sir.
So there are the two reasons why the galvanometer cannot use to measure the current. Because for measuring the current, the resistance of the galvanometer should be small. Because when the resistance will be small, there will be the more flow of current, and
Yes, sir.
the measured value of the current will be more accurate. Okay. The measured value of the
Yes.
current will be more accurate. But in the case of the galvanometer, first reason is that the small, due to the small of current, this small amount of current in the galvanometer. Suppose a small current when go in the galvanometer, there will be the large deflection of the pointer. Galvanometer is very sensitive device. Due to the small current only, the deflection of the pointer will be very large. First reason is this. That is why we do not use the galvanometer to measure the current. Second reason, the resistance of the galvanometer is large for measuring the current. For measuring the current, the device should have the minimum resistance. So galvanometer cannot be used to measure the current due to the following. Current for full scale deflection is small. Means for the small current, there will be the full scale deflection. Full
Yes,
scale
sir.
deflection of the pointer for the small current. Suppose this is the 0 ampere current, here is IG current.
Yes.
IG current is the maximum amount of current that can be detected by the galvanometer or measured by the galvanometer. IG current for full scale deflection means IG amount of, due to the IG current, there will be the full scale deflection, and the current in the galvanometer can be in only milliamperes. Very small current will be there in the galvanometer. Okay.
Okay, sir.
Second reason, resistance of the galvanometer is large. I have told you for current measurement, so it will give the significant error in the current measurement. When you will measure the current, as the resistance of the galvanometer is large, there will be some error in the measurement of the current. Now, why the voltmeter cannot be used to measure why the galvanometer cannot be used to measure the voltage? Two reasons are there. First reason is simple: voltage for the full scale deflection is small.
Okay.
V suffix G is the voltage for full scale deflection, and millivolt. This Vg, V suffix G is in the millivolt. And second reason, but see, whenever you are measuring the voltage from some device, that device should have the large resistance. Why? Because there should be the significant amount of voltage drop that can be measured by the device. But here, what will happen? The voltage is not the resistance of this device, galvanometer, is not enough for the voltage drop that we are measuring. See here, resistance of the galvanometer is comparatively small for voltage measurement. Okay, it will
Okay,
give
sir.
significant error in the voltage measurement. There will be some significant error because the resistance of this device is smaller than the required value.
Yes, sir.
Now, how we will convert the galvanometer into ammeter? Simple. Conversion of galvanometer into ammeter. You will just connect a small resistance in parallel with the galvanometer, and
Yes, sir.
you will get the ammeter. So what is ammeter? First we should know ammeter is a device used to measure the current. Okay, to convert the galvanometer into ammeter, we connect a small resistance, and that small resistance is known as shunt in parallel. In parallel of this galvanometer, we will connect a small resistance. like this. Okay, so this is suppose S is a shunt. I have written all
Yes.
the terms here. Uh, capital G, resistance of galvanometer. There will be some resistance of the galvanometer because in the galvanometer there is wiring.
Yes.
Okay, due to that wiring there will be the resistance. Shunt is the small resistance. I suffix G, I have discussed what is I suffix G. Current for full scale deflection. Now what is I? I will be the range of the ammeter. This thing is now ammeter. So range means the maximum amount of current this ammeter can measure. Okay.
Okay, sir.
Suppose range of an ammeter is 0 to 10 ampere. It means that that ammeter can measure the current from 0 ampere to 10 ampere. If the current will be 11 ampere, it cannot measure.
Okay, sir.
So now suppose range of this, not this your this device is ammeter now. This device is ammeter. What is this? Ammeter.
Yes.
It means you have just connected a shunt resistance with the galvanometer. This device will become the ammeter. And now suppose range of this ammeter I have told you is I. I is the range of ammeter. So suppose this can measure this I current. I is the current in the ammeter this time. Ammeter, not in galvanometer. Remember, so this current is going here. Also the current will be I, but this is the junction point. This is
Yes.
the junction point. Here is one resistance. Here is one resistance. The current will be divided from this junction point. Suppose I suffix G is current is going in the galvanometer.
Yes.
Remaining current will be I minus Ig,
Yes, sir.
because from this Ig current goes in the galvanometer. So remaining current
Yeah,
will be
sir.
I minus Ig.
Yes, sir.
So this is your I minus Ig.
Okay, sir.
So in the whole wire, yellow color wire, the current will be I minus Ig only. Here also the current will be Ig. Now both these resistances are connected in parallel. Means the voltage drop across this G and voltage drop across this S will be same because these are in parallel. So
Yes.
I can write the voltage drop across G is equal to the voltage drop across S. Can you tell me what is the voltage drop across this galvanometer? Voltage drop. Voltage is equal to, give voltage is equal to current into the resistance. V is equal to IR.
Yes, sir.
V is equal to IR, na?
Yeah.
So what for this galvanometer, what is IR? Ig into G, because
Yes,
Ig
sir.
is the current and
Yes.
G is the resistance.
Yes, sir.
So you can write Ig into G is equal to, what is the voltage drop for this? Hmm?
Ig into
See the current first. Only that. What is the current? Current is this now.
yes, sir.
So this is I minus Ig.
Yes, sir.
And what is the resistance? What is the resistance?
S.
S.
Yes.
So from here you can calculate the value of the shunt resistance.
Okay, sir.
Now, if you want to calculate the total resistance of this ammeter, so total resistance of ammeter can be given by one resistance is this, another resistance is this. Both are connected in parallel. In
Yes, sir.
parallel combination, resistance is given by 1 upon R is equal to 1 upon R1 plus 1 upon R2.
Yes, sir.
So resistance of ammeter is given by 1 upon R. Resistance of ammeter is equal to 1
One up.
upon G plus 1 upon S.
Yes, sir.
R1 is G and R2 is S. You can
Yes,
take
sir.
R1 as G, R2 as S, depending upon you. So your
Yes.
final resistance will be G into S, G plus S. This is the formula. So we have just converted this galvanometer into the ammeter by connecting a shunt resistance. So here you can write here voltage drop same for shunt S and galvanometer G. Across S and G, the voltage drop will be same because these are in the parallel. Okay, take the screenshot.
Done, sir.
Done.
Done, sir. Yes, sir. Done, sir.
Okay. Remember this point range of the ammeter.
Yes, sir. Done, sir.
Okay, now what we have done? We have just converted the galvanometer into ammeter. Now we will convert this galvanometer into the voltmeter.
Yes,
Into
sir.
the
Volt.
voltmeter. So conversion of galvanometer into voltmeter.
Yes, sir.
Simple. For converting the galvanometer into voltmeter, na? So suppose this is your
Yes.
galvanometer. Okay, you have this
Okay, sir.
galvanometer and you want to convert this into the voltmeter. So what you will do? You will just connect a resistance in series with
Yes,
this
sir.
galvanometer.
Yes, sir.
Finish. Okay, you have
That's
just
it, sir.
connect. Yeah, that's it. Means you will do some analysis, but if someone is asking how you will convert the galvanometer into voltmeter, then
Okay,
what you
sir.
will say, you will just connect a
The resistance
resistance
in series.
in series of the galvanometer.
Okay, sir.
But you should know the current in the series is same. In series the current is same. In parallel
Yes,
the
sir.
voltage is same. So
Yes.
suppose I suffix G is the current here also.
Yes, sir.
Here also the current is I suffix G. Here also the
Yes.
current is I suffix G because this is the series connection, and in the series
Yes, sir.
connection the current will remain same because the wire is same, the current is same.
Okay, sir.
Now this device is the voltmeter. Voltmeter.
Okay.
And now you want to find the voltage drop of this voltmeter. Voltage drop for voltmeter. For just okay, Ziyad. So see now, voltage drop in series we are calculating. Forget
Yes,
this.
sir.
I have just we are studying the moving coil galvanometer. Now we are not studying the moving coil galvanometer. That is gone. Now what we are focusing on, we are just calculating the voltage drop for this voltmeter. So voltage drop will be calculated the voltage drop in this plus voltage drop in this. Okay.
Okay, sir.
So suppose V is the voltage drop here. V is the voltage drop. Now, so what is the voltage drop for this galvanometer? Tell me. Voltage. V is equal to
Yes, sir.
IR.
Okay.
See
Yeah.
what is the current in the this is the galvanometer, no?
Yes,
This
sir.
is the resistance. For
Yes.
the voltage drop, first see the current.
Okay, sir.
What is the current across this
IG.
G? IG.
IG. Yeah.
What is the resistance?
R.
No. For this galvanometer, the
Okay. Yeah.
resistance is G.
Yes, sir.
Yeah.
Yes. Yes.
And for this, the current is again IG
Yes, sir.
and resistance is R.
Yes, sir.
Resistance is R. So
Yes.
from here you can calculate this resistance R. Very simple. V minus Ig into G is equal to I suffix G into R. So R can be calculated V minus Ig into G divided by Ig again.
Yes, sir.
So when you will divide this Ig to this V and to this Ig minus Ig, this will become R is equal to V divided by I suffix G minus this Ig and Ig will be cancelled out. Here will
Yes,
be
sir.
G. Total resistance of the galvanometer. So not the galvanometer, voltmeter. Total resistance of the voltmeter. G plus R. Both resistances are connected
Yes,
in
sir.
series.
Yes, sir.
In series, the resistance will be added up.
Is this exact same? Yes, sir.
Yeah. So resistance of voltmeter.
So in parallel, the voltage will be the same, right?
Yeah, in parallel, the voltage will be same. In series, the current will be same. Simple.
Okay, sir. Okay, sir.
In current electricity, have you means in school the current electricity is completed now?
Yes, sir.
Okay. But you should remember this. This is the from the this is the thing from the 10th class, I think. In the 10th class, we will have a chapter. Okay. In the
Okay, sir.
10th class, also we know that the voltage and resistance. Okay. So resistance of the voltmeter R is equal to G plus. Suppose resistance of voltmeter is given by R suffix V. This is G plus R. Okay. Now copy this.
Okay, sir. Done, sir. Done, sir.
Okay. So last two numerical of this chapter. Last two numerical.
Yes.
Hmm. See the first numerical. A galvanometer coil has a resistance of 12 ohm
Yes, sir.
and shows full scale deflection for 3 milliampere current. How will you convert the galvanometer into voltmeter of range 0 to 18 volt? See now, you have a galvanometer
Yes, sir.
and this G value is given as 12 ohm
Yes, sir.
and I suffix G. See, for full scale deflection, current is this 3 milliampere
3 milliampere. Yes.
and I is the range of the voltmeter. So means V is given to you. V is given to you. Means range means the maximum amount of voltage measured by the voltmeter. When you will
Okay.
how you
Yes,
will
sir.
convert this? You will connect a resistance R in the series of
Yes,
the
sir.
galvanometer.
Yes, sir.
Okay, now V is given as 18 volt.
Yes, sir.
Just apply this formula. R is equal to
V by
V by Ig
oh yeah, V by
minus G. V by Ig minus G. You will put all the values, you will get the answer. V value is given as 18.
18.
Ig is given as 3
3.
milliampere.
Yes, sir.
Milliampere means 10 to the power minus 3. Minus this will become 12. So you will get the answer 5988 ohm. How you will convert the voltmeter into means galvanometer into voltmeter means they are asking the uh, how much amount of resistance means what will be the value of this R you will connect with this galvanometer in series so that this galvanometer have the range of 0 to 18 volt. So you can write here we will connect a resistance of 5988 ohm in series with galvanometer. Simple. In series with galvanometer. Now, this question. This is based on the ammeter. Okay, they are see. They are saying a galvanometer coil has a resistance of 15 ohm. Means you have this galvanometer. This G value is given as 15 ohm.
Yes, sir.
And they are saying shows a full scale deflection for 4 milliampere current. Means I suffix G
Yes, sir.
is 4 milliampere. How will you convert the galvanometer into ammeter of range 0 to 6 ampere? Means current I means I value is given
Yes, sir.
6 ampere.
Yes.
Now how you will convert this galvanometer into ammeter? You will connect a shunt resistance in parallel
Yes, sir.
with the galvanometer.
Yes, sir.
So you have
So
to
it's in
find the
parallel.
in parallel. I have told
Yeah.
you na.
Yes, sir.
Means when you will connect the resistance in series, the
Yes, sir.
galvanometer will become voltmeter. When
Voltmeter.
you will connect the resistance in parallel, the galvanometer will become the ammeter.
Ammeter. Yes, sir.
And
So
voltmeter is
this was the main doubt I was having in school, sir.
बहुत बढ़िया डाउट था आपका. Okay. अच्छा. Means remember I can understand that मैं जब 12th में था तो मैं भी कंफ्यूज होता था इस चीज को लेके कि
Okay,
जब हम
sir.
पैरेलल में लगाते हैं तो so remember first write A for ammeter. A is the
Yes,
first letter. A is the first letter ammeter and B is after A. ABCD in ABCD B is A के बाद आता है B.
yes, I know.
तो पहले आप फोकस करो एमीटर पे. ओके एमीटर. वोल्ट मीटर को बाद में देखते हैं. सो एमीटर को क्या करना है जब आपके पास गैल्वेनोमीटर होगा. व्हेन यू हैव द गैल्वेनोमीटर एंड रिमेंबर ओनली दिस, व्हेन यू आर जस्ट connecting a shunt or small resistance in parallel means you are converting the galvanometer into ammeter. Don't think about the voltmeter. When there will be the voltmeter, remember this. You will know that ammeter में पैरेलल में लगाया था, गैल्वेनोमीटर में
Yes,
सीरीज
sir.
में
Yes.
लगाऊंगा. मींस एमीटर में सीरीज पैरेलल में लगाया था, वोल्टमीटर में सीरीज में लगाऊंगा. इस तरीके से चीजें
Yes,
याद
sir.
करी जाती है. डू यू हैव बायोलॉजी और मैथमेटिक्स?
Maths, sir.
तो यू आर अ मैथ स्टूडेंट ना, तो ओके. नाउ इट्स ओके ना?
Yes, sir.
Okay.
No.
Yeah. So now this thing. Now we have the formula for the shunt.
Yes, sir.
Okay, I will not solve this with the help of formula. I will just solve it with the help of normal method. I do not know formula. I do not know formula. So range of the ammeter is given, means range means 6 ampere current will go in this device. That this device is ammeter.
Yes, sir.
Suppose I do not know the formula. The examination,
Yes, sir.
this is the ammeter we have. I want to calculate this S value. I know that what is this I? I is 6 ampere. 6 ampere means 6 ampere current is going into the ammeter.
Yes, sir.
From here, we know that Ig will go in the galvanometer. And what will be the current here? I minus Ig?
I minus Ig. Yes, sir.
Okay. And what is I? I is 6 ampere.
Yes, sir.
This is I minus Ig. And what I have told you, in parallel, the voltage is same.
Yes, sir.
Means voltage drop across this G is equal to the voltage drop across this S. What is the voltage drop across this G? Ig into G. Ig into G.
Yes, sir. Ig into G.
V is equal to IR, na? So
Yes,
I
sir.
and R.
Yes, sir.
Voltage drop across this S, current into shunt, resistance. That is I minus Ig
I minus Ig. Yes.
into S. From here you can calculate the S. Ig into G divided by I minus Ig.
Yes.
Put all the values. You have value of Ig 4 milliampere,
4 milliampere.
10 to the power minus 3 ampere.
15.
Galvan 15.
15 ohm.
Current I is 6 minus Ig is 4 milliampere, means 4 into 10 to the power minus
Yes.
3. So can you calculate this value? You can calculate, I know.
Yes.
So there will be your answer here. This is the resistance, so your answer will be in ohm.
Okay, sir.
So you can say we will connect a resistance of this much ohm in series with the galvanometer, and our ammeter is ready. Means we can get the ammeter. Okay, Ziyad. So take the screenshot. This was the last question.
Okay,
So
sir.
now goodbye for this chapter. We will start the next chapter in the next class.
All right, sir.
And in the next class, what you should do now?
Yes, sir.
We should conduct a test, okay, for 15 minutes only.
Okay, sir.
Or I can take your Viva. Just try to prepare the chapter, okay?
So this chapter only?
Yeah, only this chapter, only this chapter.
Okay, sir.
Yeah.
So
Because
can you scroll down?
yeah, because if you are getting some doubts and all that, means I will get to know with the help of that test, and accordingly I will.
Okay, sir.
Okay, Ziyad, so now I am leaving the class. 10 मिनट पहले आपको जाने दे रहा हूँ मैं. So
Okay.
in the next class we will have
Yes.
a test of 15 to 20 minutes. Just revise your notes of this chapter properly. Have you arranged the notes in a proper